Welcome back to Finite Element Methods. Today we're talking about error estimates for the Galerkin approximation of the Stokes problem using a mixed formulation or a mixed method. I'm not going to, we've done this several times, so I'm not going to remind you what the Stokes problem is again. You're looking for a velocity and a pressure to satisfy a certain different differential equation, system of differential equations with certain boundary conditions. And so what we will, what I will remind you of is what is the Galerkin approximation of that problem. So that's given here. We're looking for an approximation of the velocity and pressure that satisfy this coupled boundary, or sorry, this coupled system of PDEs in the weak formulation. So the velocity space is what we call XH. This is a subspace of H01. Well, when I say that, what I actually mean is each one of the components lives in H01, so they have zero boundary conditions. And this is because of the no slip boundary conditions. And the pressure space comes from this space L2 with of mean zero functions. So the subspace of L2 functions that are mean zero. And our test function come from the same velocity space as the solution. This is the sort of balanced approach that we've usually been taking. And the pressure, uh, well, let's see, this test function here comes from the same space as the solution for the pressure. Let's see, we introduced two bilinear forms. The first one is a symmetric bilinear form called the A form. So that's given as indicated here. X and Q, what are these spaces? So X is just equal to the H1 or H01 space. That is the set of vector functions, each of whose components are from H01. And this Q space that's the space of mean zero L2 functions. Okay, so there's the A bilinear form. That's also clearly symmetric. The B bilinear form is a little bit weird, as you recall, because it combines a velocity and a pressure to produce a number. And the way it does it is in the following way. You take the divergence of the velocity, that gives you a L2 function, and you're going to compose that with this other L2 function Q to get a number, right? In this in the standard and usual way. Um, so that's the background. I guess I've written those spaces here, so forgot about that. You can quickly see that the velocity space is here and the pressure space is here. All right. Now we assume that XH and QH form an inf-sup stable pair. What does this mean? So we know that X and Q automatically, by their own structure, form an inf-sup stable pair. They satisfy the inf-sup condition. What we're looking for are finite dimensional approximations of the velocity and pressure spaces that also satisfy an inf-sup stability condition. The condition that we're looking for them to satisfy is one like this. If they do satisfy this, then we say that such a pair is inf-sup stable. And the good thing about inf-sup stable pairs is they will give us a lot of useful properties. The first property of which is that we know or are guaranteed that the discrete solution exists and is unique. So we talked about that. We went through that proof in detail last time. The other interesting and useful property is that it's going to give us stability, and also it's going to give us um, nice estimates. So it's going to help us with our error estimates, which is the subject of this lecture. So this condition is vital for basically everything that we do with respect to this Galerkin approximation and the Stokes problem. So the first thing I want to do is talk about how that inf-sup stable pair guarantees that we have what's called stability for our scheme. And the stability statement is given right here. It's exactly the same proof, or more or less the steps are the same as for the infinite dimensional case. And we'll repeat them here. Let's suppose that XH and QH form an inf-sup stable pair. By the way, not all pairs that you could choose out there in the universe form an inf-sup stable pair. I'll give you some examples at the end of this lecture that do form stable pairs and some that do not. Suppose that U and P is the exact solution for the Stokes problem. So that means it solves this problem where the solution are from these infinite dimensional spaces, and the test functions are from the same infinite dimensional spaces. And otherwise, the U and the P satisfy these two equations. And we're going to assume that the Galerkin approximation satisfies the usual formulation for the Galerkin approximation. Here, all we do to get a useful Galerkin approximation is we take finite dimensional subspaces that approximate X and Q, and we're going to look for our solutions there, and we're also going to use test functions from the same spaces. The first thing that we want to prove is that we have a stability like this. Oh, by the way, I want to go back a little bit. Just let me back up. I forgot to mention this before, but it is very important for the topic that for what we want to prove today. And that is a point regarding the inf-sup stability. So here's the statement of inf-sup stability. This constant in the inf-sup stability may or may not be the same beta constant that we had for Q and X. So the constant for the discrete case is likely going to be a different constant for which you can establish this inequality. The constant that you're looking for in that case, I believe, is going to be the largest possible constant that satisfies this. But in any case, that value may not be the same as for the infinite dimensional case. And so to highlight that, I've given it a tilde over top of the beta. The structure is exactly the same, so you could give them the same name. But I just wanted to highlight the fact that this may or may not be the same as the infinite dimensional inf-sup stability condition. The other point is that this beta parameter is always going to be or should be independent of H. If it's not, then you lose the ability to prove uniform estimates as we're going to try to do momentarily. So beta is likely different than the one for the infinite dimensional case, and it's independent of H, which only makes sense when we're talking about the context of the finite dimensional cases. Okay, H is like well, the mesh spacing here, and it also is directly related to the dimensions of these two spaces. Okay, so let's get back into it. So if that's true, then we can prove that for these solutions, which do depend on H, we can bound those above by something which is completely H independent. That's very important. Furthermore, we have this pseudo orthogonality condition, which turns out to be almost entirely a useless condition. And we'll try to explain why that's so. Now that condition is very easy to prove. Okay, the pseudo orthogonality. You can just take 25.2. Okay, so if we have a solution from the infinite dimensional space X and P from Q, then these two equations will hold if we restrict our test functions to the finite dimensional spaces. So I could replace these test functions Instead of using v from x, I could use v from xh because xh is a subspace of x. And I could use q from qh because it's also a subspace. So just understand that these two equations still hold if I replace the test functions with their finite dimensional counterparts. This, of course, this equation here, this system of two equations holds for these solutions in the finite dimensional space and with the test functions in the finite dimensional subspaces as well. Now, once I've replaced these with their finite dimensional subspaces, I can just subtract the two equations, okay, the two systems of equations really, and I automatically come up with something like this, okay? Um, and all you're using here is the bilinearity of both the A and the B forms. And we just use the fact that we can take a common set of test functions and we can subtract those two and get this pseudo orthogonality condition. Now, why did I state that? Well, usually that's what we do whenever we want to state the fundamental Galerkin orthogonality. It follows from something like this. But the fundamental Galerkin orthogonality is given the name fundamental for a reason. It's actually useful. This one will not be useful to our purposes for describing error estimates. And so it's a big fat fail, but it's still true. It just doesn't, it's just not that useful to us. This statement here, however, is quite useful and also quite true. And so let's prove that one. So what we do to prove this estimate, we're going to take VH and set it equal to UH in our Galerkin approximation 25.3, which is here. Just set this VH to be UH. Well, notice that if I set this to be UH, then because of this equation, that term drops away. And all I'm left with is this term and that term, which is what I have here. Okay, well, it's really just this piece of it. Okay, does everyone see that? This term will drop away because the second equation says that it's always going to be 0. Well, if I have this, this is just equal to the seminorm squared of UH. I have on the right-hand side FUH. I can apply the Cauchy-Schwarz inequality. So let's write that there, just so we know that that's what's being applied. Cauchy-Schwarz inequality. Actually, it's not Cauchy-Schwarz inequality, is it? It's actually an inequality related to the operator norm. I'll let you guys convince yourself of that. We use this inequality elsewhere in our discussion about the Stokes problem. So it's based on the definition of the operator norm. And now you see I have this term and this term appears on both sides. I can use cancellation to cancel one of them on each side as long as that solution UH is not equal to 0. That's the trivial case, so you can rule that out. So we're going to take care of the trivial case, get rid of that, use cancellation, and I immediately get this. That's one part of what we see here, but we still need a pressure estimate. To get the pressure estimate, we're going to start by assuming that we can find UH, which we always can, and we're going to solve for this pH term. Okay, if I solve for the pH term, now I'm going to estimate the stuff on the right. It's all controllable information. So I'm going to use Cauchy-Schwarz to break this term up into this term and that product. I'm going to estimate this term by Cauchy-Schwarz. Actually, again, sorry, it's not Cauchy-Schwarz. This is the operator norm estimate. And then I'm going to use the fact that I can combine these two terms using the distributive property, right? And the fact that this term here is known to be bounded by, actually, it's simpler than the distributive property. I can replace this by that term, and this becomes the norm of f. I have another norm of f here, so it's just 2 norm f, norm VH. Now let's divide both sides by this quantity. Okay. And so now you see this is exactly the same quantity that keeps appearing in our analysis. It's the same quantity that appears in our inf-sup condition. And so it's a little bit hard for me to remember the inf-sup condition, but if I start doing a little bit of analysis, I can see where it pops up. And then I realize, okay, well, I'm going to need an inf-sup condition here, assessing this term or the size of that term. The reason I need that is because I need to turn this condition into an estimate on the pressure. Okay, so I have this condition from this estimate dividing by VH, and I can do that as long as VH is not equal to 0. Okay, so actually I should say as long as VH is not equal to 0. Okay, as long as VH is not equal to 0, you can divide by that. Um, right. So now we're going to use the inf-sup condition. We know that XH and QH form an inf-sup stable pair. So that means, looking back at 25.1, that if I take the supremum of this estimate, so notice this holds for all VH in XH. So it also is going to hold for the supremum, right? Because this is an upper bound, this is a quantity, and so I know that this is the quantity called the least upper bound. This is another upper bound. The least upper bound is less than any other upper bound, right? Using its English terminology instead of the supremum, which is the kind of the French terminology of that. So this is true if I replace this for all VH by a supremum over VH right there, which is what I've done here. It's still true, but now I can invoke the inf-sup condition, and now I get a pressure norm. And so I now have a norm on pressure involving something that I know is a given in the equation. Okay, so the forcing function f is a known function, and it's known to be regular enough so that this is less than infinity. So now I have this estimate and I have this estimate. All I need to do is add them together. Before I do that, though, I'm going to divide both sides by beta. So I get 2 over beta. Okay. And if I do that, I have the estimate that I had before for UH seminorm, H1 seminorm, and PH L2 norm. I'm now going to have, after dividing by beta, that this is less than 2 over beta tilde norm of F. And I can use it as distributor property to pull this common factor out, and then you get exactly what we stated. And of course, we've already proven the pseudo orthogonality condition, so we're going to so we're done with the result. Okay. Now again, that pseudo orthogonality result is usually what is used to prove a Cea-type lemma. Okay, so we would hope that we could use that pseudo orthogonality as a jumping off point to show something like this. Okay, that u minus uh, that's the error in u, plus p minus ph, the error in p in the appropriate norms, are less than a constant times the infimum of this object, infimum of this quantity. Okay, so the reason why we call these optimal error estimates is, well, this is a Cea-type lemma allows for an optimal error estimate is because this, the error that we produce over here, is the smallest we can possibly make it for all functions VH coming out of the velocity space. So we can choose the one that generates an optimal error, like the interpolation error. And same with the pressure estimate. But this Cea-type lemma is not is kind of elusive. It's a lot harder. And so the rest of the lecture will be about trying to figure out how we can establish this. But now let's first look at how this would be done in our original Poisson problem setting. How did this work? So in the Poisson problem setting, our fundamental Galerkin orthogonality condition came very quickly for us. We just had two equations. In the infinite dimensional case, we replaced the test functions by the finite dimensional test functions, and then we subtracted, we got the fundamental Galerkin orthogonality. And we used that to produce a Cea-type lemma in the following way. So we started with the norm squared or the semi-norm squared. Uh, that's equal to A error against error. So error in both slots. Then we use fundamental Galerkin orthogonality to argue that, well, this term that we're adding on here is zero because the sum of these two objects is in VH. That was our finite dimensional subspace way back when. Oh, I should probably say, so here it's for all VH in VH. This holds true. Okay, so since this object is in VH and the first object is the error, then that just produces zero. So I haven't had added anything or I haven't changed anything. But fundamentally, you've done something very important when you add this term, and that is you can cancel off the UH here and so replace the second term with the U minus VH. Now I can do Cauchy-Schwarz on this, and I get these two terms. I can use cancellation to get rid of one of these guys on both sides. And so I get essentially Say's lemma from that point. Now, the problem is we can't use that same sort of simple trickery for these mixed problems for the Stokes problem, or these mixed formulations for the Stokes problem. We're looking for a velocity and a pressure, and this makes life a little bit complicated. We could try the same technique to see if it works out. So this object here is that object. So we might want to estimate this norm. Might want to estimate this norm. So that would be this object here. And then let's just try to add and subtract a VH term and replace this UH by the VH. So what we do when we do that is we're going to get the two terms that seems like something we would want before we're going to do Cauchy-Schwarz, but we now have these two terms here which don't vanish simply. Before this would just vanish because of the fundamental Galerkin orthogonality. Now we could hope that these two things, when we sum them together, give us zero, but they don't. So the pseudo-orthogonality doesn't help us get rid of these terms, and I don't know any other trickery to get rid of those two terms. I don't know of any way that we can see that T1 plus T2 is equal to zero, so there's really nowhere to go from here. So the homework problem addresses a way to go, and so uh, basically we have to. It's not a trick that you're going to think up perhaps on your own, and you have to sit with this problem and sit and think about it for um, a lot of time. But eventually, people who are probably a lot smarter than us and a lot more ambitious than us came up with this lemma that is going to allow us to, not by the same methodology, but by a different methodology, prove a Sayes type lemma. So this is the trick. And we're not going to prove this lemma here. I'm gonna still leave that as homework. However, the second point where we use the trick to prove the stability, we're going to go through that in detail here in the class. All right, so what's going on with this guy? What's going on? So we suppose that X, H, and QH form an inf-sup stable pair. Remember, this is a subspace of the velocity space. This is a subspace of the pressure space. Both are finite dimensional. But for the infinite dimensional uh, spaces, let's take them and make a product space. And we're going to call the product space psi. Okay, so what is a product space? That just means you're going to take pairs. One arbitrary, the first one in the pair is going to be an arbitrary element from the velocity space, and the second element, an arbitrary element from the Q space. And the way you add two objects from that space together is we're simply going to add the objects here and we're going to add the objects here separately. Okay, so that's how we can make a new linear space from two infinite dimensional linear spaces X and Q. We're also going to give this a norm. So anything from that space, let's say psi, which is a pair of a velocity pair and a pressure pair. Um, let's see, I wrote that wrong, so that should be a Q. So let's take a velocity and a pressure from that space, form a pair called psi, and here's going to be the norm for that object in this phi space. It's going to be the norm of the first object squared plus the norm of the second object squared with both of their natural norms, and then the square root of the sum. Okay, square root of the sum of those two square norms. So this is a known way of taking two linear spaces and producing another linear space. Now, it may or may not be a Hilbert space, but this is certainly a tried and true way of taking two linear spaces and combining them together to give you what's called the product linear space. Now we're going to define a bilinear form for those objects in the product space, and we're going to call it capital B. It's going to take an object from phi and another object from phi, capital Phi, combine them together to produce a real number. And the way it's going to do that is suppose I have this and this. Okay, these two elements from capital Phi. I need to combine them together somehow. So here's how I'm going to do that operation. We're going to take the velocity from the first object and the velocity from the second object and combine them this way using the A bilinear form. No problem there. And then we're going to take the second velocity or the velocity from the second object, the pressure from the first object, and combine those this way, okay, with a minus sign. We take the velocity from the first object and the pressure from the second, and we're going to add that. Okay, so the total bilinear form is all of that. So the one question that should be in your mind is it really bilinear? Okay, I've claimed it's bilinear, but is it bilinear? The answer is yes, it's bilinear because everything in sight is linear or bilinear. The A bilinear form is linear in its first and second components, so is B, and so is the second form of B. So I can easily show that this forms or makes a bilinear form. So that's the first step. Second step is, well, first of all, if we can, before I get onto that, if we can make combinations of velocity and pressure, why not do the same thing for the finite dimensional versions of those? And we can show pretty easily that if I have these two subspaces of the original spaces, then this is going to be a subspace of the thing I just created above. And it's also going to be finite dimensional if each one of these are finite dimensional. Now, the first thing I want to show is that B is continuous. That is, there exists with respect to the norm that I just created. That is, there is a constant C1 greater than 0 such that this estimate holds. And so this is a typical continuity estimate. And oops, this is a typo here. There should not be an H there. So this continuity is true if I restrict to phi h, but it's also true if I don't restrict to phi h, and it's a better result if I don't restrict. So let's not restrict that to phi h because we can prove it for the more general infinite dimensional space phi. Secondly, I can show that there's a constant c greater than 0 such that this inf-sup type condition holds. Well, I call it an inf-sup type condition. This one is on the subspace. Okay, so this has to come from the subspace, and this has to come from the subspace. That's because we want to use the inf-sup condition for our pair. Remember, we said at the beginning, these form an inf-sup stable pair. So we want to use what we know about the inf-sup stable pair, or the definition of it, to prove this result. So there's what we mean by an inf-sup stable pair for QH and XH. So somehow what we want to do is, with this new definition, we want to translate that inf-sup stability between QH and XH into this inf-sup stability here. Okay, so this is kind of like an inf-sup stability for the B problem. However, you should notice something that makes it not like the normal inf-sup condition that we've been dealing with. That's because this bilinear form B is really a balanced symmetric bilinear form. Well, is it symmetric? It's not symmetric, no. But it's balanced in the sense that it takes objects in both locations from the same space. Okay. In general, it's taking them from where? Both the first and the second objects are from this capital phi space. So it's a little bit different than the inf-sup condition that we stated earlier because that was for lowercase b bilinear form. The first element was a velocity and the second element of that was a pressure. Here, it's the same. They're the same, or the functions are coming from the same spaces. So this follows, you can prove from the inf-sup condition for XH, QH. Now, finally, if U and P are the solutions, okay, to the solution pair for the Stokes problem, and phi H is the solution pair for the Galerkin approximation, respectively, then we can show that we get a fundamental Galerkin orthogonality type property back. Okay, so this one is a fundamental Galerkin type orthogonality. And it's not hard to show because this should follow from something like the pseudo orthogonality property that we had above. Now, why is this one going to be more useful to us? Well, we'll see why when we go to prove the next result. Now, I'm not going to prove this result for this B bilinear form. I've given you some hints in the homework, and I hope that I've stated the problem correctly, but you can let me know if you have any questions about it. However, once we have this result, we can use it to prove exactly the Cea-type estimate that we had going before, or that we were trying to prove before but had failed. And so that key, that little lemma key, is going to open the door for this Cea-type result. All right, so the next thing we want to do is establish this Cea-type lemma. And I just realized here, looking at the hypotheses of this theorem, I haven't really stated my assumptions here very well. This is kind of outside my character. So let me tell you what the assumptions are. Basically, we're just assuming that that XH and QH form an inf-sup stable pair. That allows us to establish this previous lemma. Okay, so basically I should say we're at least assuming the same hypothesis as the last lemma. And under those conditions, we now have this result. All right, so it comes in a couple of steps. There's some tricky parts here and there, so bear with me. Okay, so here's the proof. So let VH and QH be arbitrary velocities and pressures. And we're interested in approximating this error, which is the sum of these two errors. Okay. So let's add and subtract a VH here and add and subtract a QH here and use the triangle inequality. If we do that, then we have, instead of one term here, two. Instead of this term, we have two. This is what we want. This is also what we want. And we need to figure out how to deal with this and figure out how to deal with this. Okay. Now, if I define an object called, what do I want to call it? Squiggle H, which is going to be VH minus UH for its first component, and QH minus PH as its second component from this space phi H, then what do I have in this position and this position? Well, if I looked at how I defined the norm previously, then this is a part of the norm and this is a part of the norm, except the norm was the square root of these two squared. Well, I can use a Cauchy-Schwarz inequality. Basically, this is like saying I'm using Cauchy-Schwarz in this sense. I have A plus B, and I want to know, is that less than or equal to square root of A squared plus B squared? So that's a very simple application of Cauchy-Schwarz. And the answer is yes, it's true as long as I put a constant here of square root of 2. So this is a very simple application of Cauchy-Schwarz. And that's what I've done here and here. Okay, using the definition of my phi norm and by recognizing this or defining this squiggle h as this function. Okay, so that means this is the first and that's the second part of that norm. Okay, so that guy is going to be A, and this guy is going to be B. And I want to show that that's less than the square root of A squared plus B squared. Well, it's a simple application of Cauchy-Schwarz. And I get it. All right, so let's continue on. So now I have the error is less than these two terms, which are the terms I want. So that was that term and that term. And these two terms here are combined and estimated like this. So now I'm going to use that inf-sup condition that I had for the capital B bilinear form. That was 25.8. The first two terms I'm going to leave the same. The second one I can show is less than 2 over C0, or sorry, square root of 2 over C0. Okay. This C0 is the C0 that was involved in 25.8. If you go back and look at it on the, well, let's do actually that. So there's that C0. I'm just taking that C0 and bringing it over here by dividing both sides. And I'm trying to estimate this object by this supremum. Okay, so that's what I've done here. Okay, I'm estimating this object by that supremum. Okay, we're almost done. So we have the two terms that we want. That's that and that. Now we're going to use that fundamental Galerkin orthogonality involving the capital B bilinear form. But I'm going to use it in the following way. Phi minus phi h. Okay, that's the error. That's what I need in there. Phi minus phi h. Except I'm going to put a minus sign on that. That's fine because this is a true bilinear form and the minus can go in or out, doesn't matter. That is to say, this is true. If I put a minus inside, this is still true because that minus can come out and it's still going to be 0. I hope you see what I did there. Okay, so I added this term. This term is just going to be equal to 0. Okay, I've just added 0, so I'm not doing anything wrong. Okay, that's just equal to 0. Well, let's write it like this actually. That whole term is just 0. Okay, so that's the Galerkin orthogonality condition. Okay, otherwise nothing else has changed. Now, let's add these two terms together. What do we get? Well, it's bilinear, so if we add them together, we're going to get this weird looking term here. Okay, that weird looking term there. Um, what is that term? Let's give it a name. Let's call that R. Okay. It's not from the finite dimensional space capital uh, phi h. It's from the infinite dimensional counterpart capital phi. All right, so how do you add stuff together from that space? It's the way I always do it when I make a product space. I have to add the velocities together, and then I have to add the pressures together separately for all these three variables. If I go back and look at the definition of this guy, what was it? It was here. And then phi and phi h, according to my definition above, that's just going to be, well, phi is just going to be the solution to Stokes' problem, and phi h is the solution to the Galerkin approximation of the Stokes problem. When I combine those together, all right, and I do this, uh, well, it's these two are added and this one subtracted. I get this and that, right? So now a good thing has happened because what I wanted to do was get rid of the UH, just like I did in my simple proof before for the Poisson problem. I get rid of the UH and I also get rid of the pH. And so what I'm left with is VH minus U and QH minus P. That's exactly what I want because that's what's appearing here and here. U minus VH and P minus QH. Okay, that's good. But I'm not ready to identify those yet. Just keep in mind that the R has this as its velocity term and this is its pressure term. Okay, so now I haven't changed anything yet. I've simply identified this R by first adding these two terms together, the two numerator terms, adding them together, and identifying this object as R. So nothing has changed, just some identifications, just some notations. Now I recall this object is continuous. Okay, so it has a Cauchy-Schwarz type of property associated to it. And I think I'm missing a term here. Yeah. So I'm missing a C1. When I apply that continuity, I have to use the continuity of the problem that was available to me, and it comes with a, a constant C1, 25.7. 25.7. I forgot my C1. Now that's been rectified. It's back. Okay. When I use that continuity, I can cancel the two bottom terms, right? From the quotient, uh, numerator and denominator are the same thing. I can cancel those. Once I do that, then there's nothing really to take a supremum of over anymore because this thing is completely independent of phi h. Okay, so that's fine. I can just get rid of the supremum, but I am missing a C1 here. So let's put that in. C1 is there. Okay, I think we're okay now. And what do we have here? Okay, so now I have a norm. This is almost looking like these pairs out front. This is equivalent to saying I have something like this. a squared plus b squared, is that less than or equal to some constant times a plus b? And the answer is yeah, that's also true. So we can replace this object here by a constant times that object. We already have a constant that was there when we combine them together. Now, first of all, you shouldn't be worried about the fact that this has the wrong sign as this one out here. It's not a problem because I can simply add a minus sign, just change their order, right? And the same thing with this one. Just because they look like they're not the same, they actually still are. In any case, using this estimate here, I can show that this is less than a constant times all this. I have another constant that's already there, so that's fine, no problem. This just gives me one big constant. But in any case, I have exactly what I wanted to prove, um, because now this is arbitrary and this is arbitrary. I can take the infimum for both objects and I get the Cea-type lemma that I wanted. Okay, so this is proven. Finally, let's finish up here. Finish a little early. What inf-sup stable pairs are there out there in the universe? And what pairs are maybe not inf-sup stable? One of the most famous ones that is inf-sup stable is what's called the Taylor-Hood element. So for the Taylor-Hood element, what you do is for the velocity space, you're going to take these spaces M0R. So remember what this space means. It's the piecewise polynomials of degree R that are zero on the boundary. And so this superscript D means that you take every component and require every component of your velocity space to come from this space. For the pressure, we're going to take the same space, only with 1 degree lower polynomials. Okay, so the polynomials here are degree R. Here it's degree R minus 1. And we're going to intersect that with the mean zero functions. Okay, let me put mean zero functions over omega, our space that we're solving here. Okay, and so all this means is you're going to take polynomials of degree R minus 1, or I should say globally continuous piecewise polynomials of degree R minus 1, but we're going to get rid of any of the functions that aren't mean zero from that space. Does that leave any functions left? The answer is yes. There's plenty of functions left in that space that are mean zero. So this pair together is known to be inf-sup stable as long as R is bigger than or equal to 2. So that means that these are piecewise polynomials of degree 2 or better, and these are piecewise polynomials of degree 1 or better. This forms an inf-sup stable pair. So what pairs would not be inf-sup stable? Okay, so not inf-sup stable pairs. So what pairs are not inf-sup stable? Well, if I take, say we can make this easy, there are lots and lots of pairs which aren't inf-sup stable. But one of the ones which is right away not inf-sup stable, okay, is if we take the same degree polynomial here as in the pressure space. If I take R to be the same, or the degree of the polynomial that is to be the same here and here, then that gives me a pair of velocity subspaces and pressure subspaces which taken together do not satisfy the inf-sup condition. Okay, so that is also well known. And then of course there are lots more pairs out there which aren't inf-sup stable. I don't know all of them in particular, Uh, one of the ones that is really well known is if you just want to use piecewise linear for both the velocity space and the pressure space, do you get an inf-sup stable pair? The answer is no. You don't get an inf-sup stable pair for that case either. All right, so that's basically it for our discussion about the Stokes problem and the Galerkin method for the Stokes problem. And so I don't know exactly where we're going to go in our last lecture, or maybe if we do a lecture on the final exam time, might pair those up and do two in a series. But we'll see. I have to kind of think about how motivated I am and how ambitious I am. But in any case, we've certainly settled the issue with the Stokes equation. I might do Navier-Stokes. I might decide to do the discontinuous Galerkin method to show you how that works for the Poisson problem. I have to think about that. But in any case, that's it for today's lecture. Uh, it's my early Thanksgiving gift to you to end 20 minutes early. Is that right? 20 minutes early? Yeah, I think so. Um, and so you can turn your cameras on and I can take your questions.